one is the U1 of E and M. Okay? So that's how you call the group theory stuff. Okay. Questions about that? Anything else? No. I'm going to stop the gauge theory stuff there because I really, really want to do this path integral stuff. And so here's the start of the path integral stuff in today's. Okay. Path integrals in field theory are absolutely required for things like Yang-Mills theory. There's been nobody's quantized Yang-Mills by doing canonical quantization. The gauge constraints, the gauge aspects of it are too painful. And I've skipped over much of that in our treatment of it. It's a little bit painful in QED, but it's too painful to do except in path integrals. So they're absolutely needed. But they're also the best way to do things, really. And for our purposes, they're also very important for making the connection to statistical mechanics. And we'll say a little bit about that as we go. So what I'm going to do is I'm going to do a quick treatment of quantum mechanics. It's probably 1 day's worth of quantum mechanics to build up all the techniques that I need, which are a lot of functional techniques that you often don't see in the quantum mechanics treatment. And then do field theory the rest of the time. Okay, so this will be our last big block. Okay, and what I want to do is I want to start off just doing integrals. So path integrals, you need to do integrals. So here's our basic integrals. Okay, and we build everything out of these guys. Let's start with the simplest Gaussian integral. So these are all Gaussian integrals. Okay, so let me define I of A is integral from minus infinity to infinity dx e to the minus 1/2 ax squared. So that's a Gaussian integral over the variable x. That's a trivial one to do. 2 pi over a to the 1/2. Good. Now we're going to do variations on an integral. Sounds like a great talk. Okay. So here's variation number 1. I guess I've labeled them A, B, C. So let's define I sub j of A, which is integral minus infinity to infinity dx e to the minus 1/2 ax squared plus jx. Okay, so now it's a shifted Gaussian. There's this little shift, and the way you solve it is you complete the square. You write this as integral minus infinity to infinity dx e to the minus 1/2 a x minus j over a squared e to the plus j squared over a squared, and there's a 2 there. Okay, so if I expand this out, the cross term here gives me the jx piece. Then there's the square of this, which cancels that, and I've got my same old integral. Okay. But since I'm integrating from minus infinity to infinity, if I shift it by j, I get the same answer out. So this is some, this is some x prime, and this is dx prime minus infinity to infinity. And so I get the same old integral back again. And so this is equal to 2 pi over a to the 1/2 e to the j squared over 2a. Okay, do I have it right? There's only one power there. Just those of you taking notes, I just erased a 2 right near where that flashing box is. Okay, so that's right. So here's how we're going to use this guy once we make it a little bit fancier. If I want the integral from minus infinity to infinity dx of x to the n e to the minus 1/2 ax squared. Okay. Well, that's equal to the nth derivative with respect to j, I sub j of a, and then you set j is equal to 0. Okay, so if you go back to the original definition, every time I take a derivative with respect to j, I bring down a power of x. So I take n derivatives, I bring down n powers of x, and so I can do all this integral by just taking derivatives. Okay, and that's what we'll do in field theory. That's going to be a big field theory trick. Okay. Okay. So now, B, generalization B. Let me let j goes to ij. Okay. So then we have integral minus infinity to infinity dx e to the minus 1/2 ax squared plus ijx. Well, that's, again, 2 pi over a to the 1/2 e to the minus j squared over 2a. Okay, that's good. Next generalization, we're going to take a goes to minus ia. Okay, so integral minus infinity to infinity dx e to the I. Now I've got I in front of everything. 1/2 ax squared plus jx is, when I just take in the answer, I'm going to do the same thing. So this is really an analytic continuation. It's 2 pi I over a to the 1/2 e to the minus I j squared over 2a. Okay, so I just put ia into that formula there, minus ia there, and that brings me these i's in the numerators. Okay, good. Now, let's try many variables. Okay, so I'm going to take x goes to xi with I is equal to 1 up to n. This constant a will turn into aij with I and j up to 1 to n, and I'll choose this to be symmetric. Okay, actually I don't have to choose it to be, it is automatically by, since it's the, yeah, because it's, you'll see when I write it down it has to be. And j is going to turn into some ji. Okay, so then now we're getting a little bit fancier. I have the basic Gaussian integral is then minus infinity to infinity dx1 up to dxn e to the minus, no, I'm back to being real here, so xi aij xj plus ji xi. Okay, so that's what we have to do now. All right, so let's do that. The way to solve it is we can diagonalize A. Okay, so we let y is some oij xj, or xj is o minus 1, well, actually, I can take the labels off, y, so it's just a matrix. And so then the piece that I have there, I have x transpose a x, it's transpose, not dagger, is x o minus 1 and looking at this, I'm all right. O x o a o minus 1. Okay, actually all I've done here is I've not done anything. I've just put in o and o minus 1. Okay, so I've just taken this thing, o minus 1 o, o minus 1 o, and added it. It looks to me like my notes should have transposed backwards, but am I right? No, that's right. This is y transpose, and this will be chosen to be diagonal. This will be a diagonal. Okay? So this is diagonalized by, it's an orthogonal matrix, since it's a real symmetric matrix to start with. And then we also use integral dx1 dxn is the integral dy1 up to dyn. If this is an orthogonal transformation, that's true. So this results in then, implies that that integral is the dy1 up to dyn e to the minus a half y transpose a diagonal y. And then I have to do, this is then minus j prime y. Okay. Jx is j o minus 1 y is j prime y. Okay. People following the algebra? Okay. The beauty of this now is that this is just n single one. Since this is diagonal, this is just all these exponential factor. This is y1 squared y1 with a1 there, etc. So they're all independent Gaussian integrals, so we've already done that. So this is then the product of I is equal to 1 up to n of 2 pi over the a diagonal I, so whatever the diagonal element is, to the 1/2, and I get e to the minus 1/2 j prime I a diagonal minus 1 a j prime j, where this matrix is just the matrix 1 over A1, 1 over A2, dot, 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 1 over AN down at the bottom, zeros on the off diagonal. I'll just take 1 over A's for all of them. Okay? Everyone see that step? That's probably the one that requires, you have to see that all these things factorize well, and so it's just each of these with A1, A2, A3, etc. comes out. Okay. Okay, so that's the integral. We write this in a fancier form. It's the 2 pi's just become 2 pi to the n over 2. That's there. The product of the diagonal elements we'll write as the determinant of a diagonal. It's raised to the 1/2 power. Okay, so the product of a diagonal 1, 2, 3, etc. is that. And this is then multiplied by minus 1/2. I'm going to go back to the original j's. J O minus 1, a diagonal minus 1, O J. Okay, and our last trick is to get away from this diagonalized matrix and back to the original one. And to do that, we need 2 steps. We need determinant A diagonal is the determinant of A, because determinant of A diagonal is determinant of O, where is it? OA, O minus 1. And the property of the determinants, the O's cancel each other, and so then we get the determinant of A. And the other thing I need is O minus 1, A diagonal minus 1, O is the original matrix inverse. Okay, that's a little less obvious, but let's just check it. If I take A minus 1 and multiply it by A, I'm claiming A minus 1 is O minus 1, A diagonal minus 1, O. And A written in terms of A diagonal is O minus 1, A diagonal, O. So these guys cancel each other. The A times A diagonal, A minus 1 is 1. And then the final O's cancel. So that's 1. So if A and A are diagonal or are related by this rule, then that's the inverse. Okay? And then I can end up with, so this implies then integral minus infinity to infinity dx1 up to dxn of e to the minus 1/2 x dot a dot x. Okay, so that's there's indices there, plus j dot x is 2 pi to the n over 2, the determinant of a 1/2 e to the 1/2 j dot a minus 1 j dot j. So again, the matrix sum is there. Okay, and I guess I'd hope to get a little further. Let's do the final one. This is the big one, the one we use. Let's call it, define it z of j is integral dx1 up to dxn. And now I'm just going to put those factors of I back in the same way I did before. E to the I 1/2 x dot a dot x plus j dot x equals, it's then 2 pi I to the n over 2, determinant of a to the 1/2 e to the minus I over 2 j dot a minus 1 j. Okay. All right. So there it is. Don't ever forget that one. Okay. That's the basis of all path integral methods, functional methods. And we'll come back next time. What we'll do next time first is I'll just do some little practice calculations to remind you of this integral. We'll then do path integrals in quantum mechanics, including calculating matrix elements of the harmonic oscillator. We'll do harmonic oscillator matrix elements. You will then, after that, do a few more matrix elements on the harmonic oscillator, and then we transition to functional methods in path integrals in field theory. Okay, so that's where we'll go. Okay, good, thank you.